Hey there, welcome back to Calculus. We're going to continue our work in Chapter 2, looking at Section 2.5 now on continuity. So you can see the objectives of the video lecture are written there for you. I want to define what I mean by continuity, both at a point and on an interval. So a function may or may not be continuous at a point or may not be continuous on an interval. I want to tell you what I mean by that. In the event that a function is not continuous at a point, that discontinuity might be removable or not removable. So I want to tell you what I mean by that and show you some examples. And then I want to list some families of continuous functions. Lots of the functions that we'll work with in this course are continuous. And then we're going to end by stating an important result about continuous functions called the Intermediate Value Theorem. Try to give you some sense of what it means. So to kind of motivate the whole thing before I even scroll down to the definition, we saw last time that for many functions, polynomial functions, for example, it's kind of the best kind of limit when you want to take the limit of a function as x is approaching a, that principle that kind of allowed us to just directly substitute in a as long as we weren't dividing by 0. In many cases, we saw that the limit was just the function value. So this is sort of the best kind of limit. The best kind of limit is the kind that you can calculate just by evaluating the function. And very briefly, that's what it means to be continuous at a point A. A function is continuous at A when this limit exists and equals the function value. All right, so let me scroll down a little bit. I've got the fancy definition from the book here for us. So this is clipped from the section 2.3 in your book, and it says a function is continuous at a number a, continuous at a point, if what we just wrote is true, if the limit of that function as x approaches a is equal to f of a. So I'm going to kind of break that down, and it means, among other things, this is maybe going to seem a little bit redundant, but so what does it mean to be continuous at a? Well, first of all, a has to be in the domain of the function. F of a has to be defined. Yeah. Second of all, the limit has to exist. You have to have a limit there. The limit can't fail to exist. Two-sided limit. And then thirdly, this is the kind of redundant part, that limit can't just be any old value. It actually has to be the function's value at a. Okay, so if you have a function defined at a, the limit exists, and the limit is equal to the function's value, then you're continuous. You're continuous at that. So how can a function fail to be continuous? Well, it must fail one of these criteria. Maybe it's not defined there. Yeah, if it's not defined there, it's not continuous. Maybe the limit doesn't exist. Maybe the limit exists, but it doesn't have the right value. Let's take a look. You can kind of see these things. If you're looking at a graph of a function, it's once you have your head wrapped around it, it's not bad to decide where the function is continuous or not. Here, I need to shrink this a little bit, because on this screen I didn't write quite small enough. Hopefully you can still see all of that. So I've got this fictitious function drawn there. Fictitious, I don't mean it's fictitious. I mean, there it is, but I don't have it defined by a formula, right? So I just drew this graph, but it passes the vertical line test. And you can see that at these four numbers, A1, A2, A3, and A4, there's some kind of interesting phenomenon going on. And those four numbers are kind of illustrating, in some sense, I don't mean this in a complete sense, but in some sense, this is the ways that a function can fail to be continuous at a point. So let's just look at them one at a time. Let's look at the A1 first. So I'm looking at this input A1, and I can look at the graph and see that the limit doesn't exist there. The left-hand limit exists, the right-hand limit exists, but they're not equal, so the two-sided limit doesn't exist. All right, so it's discontinuous. The function is discontinuous at that number a, and we're going to call this, people usually call it a finite jump discontinuity. I'm just going to write jump discontinuity. So discontinuous meaning the opposite of continuous. And we're not continuous at that number a. We have a finite jump discontinuity. If you like to think about it, reading the graph from left to right as x is increasing, which I always encourage you to do, read graphs left to right as the input increases. So the outputs were sort of happily approaching whatever this y value is here, and then they quote unquote discontinuously change to that y value down there. So that's why they call it a jump. So the values changed in sort of a non-continuous or smooth way. How about at A2? The function's also not defined at A2. At A2, it's just not even defined, so it's not continuous there. It's not continuous because it's not defined. There is no value. That's a vertical asymptote there at A2, so there is no function value. At A3, if you look at A3, the limit exists. The limit exists. The limit as x goes to A3 of f of x. It's the two-sided limit exists, but it doesn't equal the function value. That little solid dot down there says that the function value is less than the limit. Yeah, are you looking right here in this picture? So the limit exists, but it doesn't equal the right value. So it's discontinuous. And then over here at A4, it's kind of like that sine of 1 over x example that we looked at. At A4, the limit just flat out doesn't exist, but it doesn't exist for kind of a different reason than it does at A1. This function is one of those waves that's oscillating faster and faster, so the function's just not getting close to any value there. Yeah, so it's not, doesn't have a left limit, it doesn't have a right limit, it just doesn't have a limit there. Good. So those, in some sense, that's kind of the 4 ways that a function can fail to be continuous. Its limit can just flat out not exist. It cannot exist because left and right-hand limits aren't the same. It might not be defined at the point, or the limit might exist, but it's not the right value. All right. So in that third case, at A3, people call this a quote-unquote removable discontinuity. It's a removable discontinuity because if I was willing to change the value of the function at A3, I could make the function continuous there, yeah? If I took, instead of saying the y coordinate at A3 is right there, if we put the y coordinate right there, then we would make the function value be the right limit. And so we'd get a continuous function. Okay, A1 and A2 and A4, those are called non-removable. I don't know a good way to write this here, but all 3 of those things are non-removable. Maybe I'll try to write it over here. Non-removable discontinuity. Jump discontinuity, you can't redefine the function anywhere to close that gap. You can't define f at A2 to have any value that's going to make the limit exist that value. You could define f at A2, but since that thing that has an asymptote there, you're not going to get the limit to equal the value. And in A4, the limit just flat out doesn't exist. All right. So 3 of those 4 discontinuities are non-removable. Good. Oops, sorry about that. We can rescue something here. The book, we won't dwell on this too much in this course, but just to mention it, you can speak about continuity from one side or another, a function being continuous from the left or continuous from the right. So I just kind of got a shrunken version of our function we were just looking at here. At the point A1, that function is continuous from the right. If you take the limit as x approaches A1 from the right, then the limit is equal to the function value, but it's not continuous from the left. It's not continuous from the left because the limit doesn't equal the function value from the left. So sometimes if you're only considering limits from one side or another, you can speak about one-sided continuity. All right, so that's just kind of a quick aside. What does it mean for a function to be continuous on an entire interval? Well, it means it's continuous at every point on that interval. Here again, I've got to kind of shrink if we're going to be able to see all of this at the same time. But our function above is continuous on the interval. Let me just kind of color them as we talk about them. I'll make the pen a little bit better size. This function is continuous from negative infinity all the way up to the point A1. So that's how I'm writing down here in interval notation. Negative infinity to A1 with an open bracket. And then if you're not familiar with this union symbol, it's just the mathematical or. So it's continuous on that set together with, let's color another one. The interval from A1 to A2, it's continuous because for every point x between A1 and A2, not including them, that's what the round parentheses mean, it's continuous. All right, and well, maybe the colors aren't doing all that much for me, so we'll just kind of continue along. Between A2 and A3, it's continuous on any interval between its discontinuities. So that particular function is continuous on 5 intervals, from minus infinity up until the first discontinuity, and then between the first and second, between the second and third, between the third and fourth, and then from the fourth one on. So 4 numbers cuts the number line into 5 intervals. So continuous on an interval just means continuous at every point on it. And if somebody says a function is just flat out continuous, they mean it's continuous on its entire domain. Okay? Let's look at an example. I got a function here, f of x is x plus 7 over x minus 5, and my question is that function continuous at x equals 5? Maybe you should pause the video and try to answer it. Is that function continuous at x equals 5? I hope you paused it, and I'm going to answer no. No, it's not. Why? Because f of 5 is not defined. Five is not in the domain of that function. If you're not in the domain of a function, the function can't be continuous at you. Okay, so that's it. How about example 4 down here? Notice it's a very similar function. I wish I would have. In fact, I'm going to change it. I'm going to change its name to g of x. So g of x is x plus 7 times x minus 5 over x minus 5. And I'm asking the question, is it continuous? You can pause and think about it. I'm going to write the answer right now. No, it's not, and it's the same reason. G of 5 is not defined. So it's sort of a repetitive question, but let me add to these 2 examples while we're still looking at them both at the same time. Let me ask you this, in example 3, is it removable? Is that discontinuity, could we define the function at 5 in such a way to make it continuous? You can go back into the lecture 2.3 videos if you like, but this function, x plus 7 over x plus 5, we showed that its left and right hand limits weren't the same. The limit as x goes to 5 from the left of this function, values that are less than 5, is negative infinity. But the limit as x goes to 5 from the right of f of x was positive infinity. So it has a vertical asymptote there. So this is not removable. There's no way to define the function f at 5 to make it continuous at 5. What about g? I think you can see what the nature of my example is. G, if x is not equal to 5, g is just equal to the function x plus 7. Yeah, so by that limit property, if we take the limit as x goes to 5 of g of x, let me just write briefly, then we're going to get the limit as x goes to 5 of x plus 7. That is, we're going to get 12. So we can remove this continuity if we define, because remember, 5 is not in the domain of g, but if I put it in the domain by saying, well, I'm going to make g of 5 equal to 12, then we remove the discontinuity. Does that make sense? That's what the nature of a removable discontinuity is. I'm looking at my whiteboard and it looks a little messy here, but I hope it made sense. All right. So what functions are continuous? What functions are continuous? Let's look at these 2 theorems at the same time. Well, basically all the functions that we're going to work with here in this calculus class are continuous on their domains. So all polynomial functions. So what I'm listing here is functions that you can take limits of by just plugging in. Just plug in the value. Just make sure the value's in their domain. Yeah. So any rational function. The example we were just looking at were rational functions. 5 wasn't in their domain though. The x minus 5 in the denominator means 5 is not in that domain. But at any point in the domain, a rational function is a continuous function. Radical functions, I mean root functions, square roots, cube roots, and so on. Again, no negatives under even roots. So we're staying in the domain. All the trigonometric functions. Sine and cosine have domain all real numbers. Tangent, cotangent, secant, cosecant, they don't have domains that are all real numbers, but at any point in their domains, their graphs are continuous. The functions are continuous. If you're familiar with the inverse trigonometric functions on their domains, they're continuous. Exponential functions, logarithmic functions. So these are important families of functions in our course and in all of calculus, all of mathematics, and they all have this very luxurious property that the limits at any point in their domain is just the function value. So sort of an intuitive way to think about continuity, since the limits exist, is that if you change the input a little bit, you only change the output a little bit. That's kind of another way to think about continuity. So for everybody in all these families of functions, if you are at some point in their domain and you change that input value by just a little bit, the output values will change by a little bit. Okay? Here's another important property, Theorem 8, about continuous functions, that you can interchange them with limits. So if you're taking the limit of f of something, and f is a continuous function, you can take the limit of that something and then plug it into f. All right, so continuous functions interchange with limits. Let's do an example showing you what I mean by that. Here I'm taking the limit as x goes to 0 of the cosine of this rational function, pi plus x cubed over x squared plus 3. All right. Well, according to the box above, we can't see it anymore, but it said that the cosine is a continuous function. So according to the theorem that we're still looking at, I can take this limit by taking the cosine of what I get taking the limit as x goes to 0 of pi plus x cubed over x squared plus 3. Yeah, and so using our limit laws, pi plus x cubed as x goes to 0 just goes to pi. And in the denominator, x squared plus 3 goes to 3. So you just have to take the cosine of pi over 3. And maybe you've got it memorized, I hope you do, from a unit circle, or if you need to look at a unit circle, you could use a calculator in radian mode, but it's going to give you a decimal approximation, but this one will actually be an accurate decimal approximation, because the cosine of pi over 3 is, did I stall long enough? It's a half. So that illustrates that theorem up there. I want to take the limit of the cosine of something. Okay, well, take the cosine of the limit of that thing. You can always do that. It's because cosine's continuous. So same thing if cosine got changed to sine, tangent, cotangent, provided what's in here approaches their domain, something in the domain. Okay. Let's look at another example. Here I've got a piecewise function, and I'm asking, where is it continuous? All right. Well, for x strictly less than 0, it's given by the sine function. That's continuous. So I know it's continuous at least on the interval from minus infinity to 0, not including 0. It's also got to be continuous on the interval from 0 to infinity, because from 0 to infinity, this function's just a polynomial. Polynomials are continuous. So the only possible place where it could fail to be continuous is at x equals 0. We have to check x equals 0. So what does continuity mean? It means that the limit exists and equals the function's value. What is f of 0? F of 0, which formula do you use? So right, in a piecewise function, this is what makes a piecewise function piecewise, is there's an extra step when you evaluate them. There's two formulas here. Right? You can't use them both. The function has to output one and only one value for a given input. So that's what these conditions over here. When you're using a piecewise function, you have to take your input, 0 in this case, and you have to ask yourself the question, well, which of these two conditions does my input satisfy? Is 0 less than or equal to 0, or is it greater than 0? No number can satisfy them both, because otherwise we don't have a function. They have to be disjoint sets. And in this case, it's the first one, yeah? 0 is less than or equal to 0. So I'm going to take the sine function to evaluate this, taking the sine of 0, which from my unit circle is 0. So f of 0 is 0. So if this is continuous at 0, we need to have that be the limit, right? This is a piecewise function, so we have to do that limit one side at a time. I have to first take a look at the limit as x goes to 0 from the left, because it's not given by the same formula. And on the left, values of x that are less than 0, we're using the sine function, right? The sine function is continuous, so this limit is just the sine of 0, that's 0. Okay, so far that's looking good. We want this limit to equal the function value, but we also have to take the limit from the right. And from the right, sorry about all the scrolling, I hope I'm not making you seasick, but from the right, I have to use the formula 1 minus x squared. Right? Because that's what's governing this function if x is bigger than 0. 1 minus x squared is a polynomial, so its limit is its value. That's 1. That's not good. 1 is not the same as 0. So this thing is not continuous. Oops, I didn't need that period there. It's not continuous at x equals 0. So it's a lot of calculation. I forgot what the question was. Where is this thing continuous? Well, it's on this interval. It's continuous on the interval from minus infinity to 0. This is my final answer. Minus infinity to 0. Again, this union symbol, read it together with. Minus infinity to 0 together with 0 to infinity. That's where that function's continuous. Okay, so it's not continuous on its whole domain. It failed to be continuous at one point. We needed both of these limits to equal 0 if it was going to be continuous there. Cool. Okay. Well, one more result here. I'll try to not make it too long. This thing, it's kind of an interesting thing. I would never want to give a calculus course without stopping to tell the students in the course about the intermediate value theorem. It won't be a super practical tool for us, although if you're interested, maybe in an office hour, we could open up a Desmos window or something like that, and I could show you how to use this theorem to approximate solutions to equations to, well, really kind of any degree of accuracy that you want. But for right now, let's just kind of take a look at it and then give some intuitive idea of what it means, and then we'll end with just one more example. So the intermediate value theorem, what does it say? So well, you can look at it there. It's talking about a continuous function on a closed interval, right? So can I, if I just highlight as we speak about the theorem here, oops. So we're starting with some function that's got to be continuous, not on the whole real line, but at least between two numbers a and b. And you guys remember what these square brackets mean? It means that the numbers a and b are included. So it's continuous, say from the right at A and from the left at B. Stop the video and make sure my right and left made sense there. Okay, and then you take any number between the outputs of A and B. So down here in this picture on the left, it's showing it like f of A is less than f of B. So they're picking the number n between them. In the picture on the right, it's still the same, that f of A is less than f of B. Sorry, I misunderstood the picture. They pick some number n in between them. So you pick some value between the value at the endpoints, okay? The value of the endpoints not being the same, so that they're different numbers. One of them is bigger than the other. Then you have to be able to find some number in the interval between A and B whose output is the number you picked. All right, so I kind of feel like I butchered that as I was reading it out loud. I wish I could go back, but I'm not going to try to edit this long video. But let me do say this: that the intermediate value theorem is saying that a continuous function takes on every value between any two values that it takes on. So if it has some y coordinate on its graph like f of A, and it has a y coordinate on its graph like f of B, then every y coordinate between f of A and f of B is going to be on that graph. So n is just one of them. And the picture on the right is saying, like, when you're given an n, there might be a whole bunch of y coordinates on that graph, but there's got to be at least one. A continuous function takes on every value between any two of its values. So let me interpret that in terms of a sort of a pseudo-physics example here. Maybe you, like me, believe that temperature, say starting at some time in the morning, 6 o'clock in the morning or whatever you like, is a continuous function of time. Yeah. So here in Arcata, in the northern hemisphere, in the summertime, even though it's not a huge change usually, starting around 6 o'clock in the morning, the temperature is going to rise until some point later in the day, usually early in the afternoon. And that temperature rises, I claim, continuously. In the intuitive sense that if the amount of time that goes by is just a little bit, then the temperature will change just a little bit, yeah? The temperature doesn't jump values discontinuously. So let's say these are sort of our Arcata realistic numbers, that it's about 55 degrees at 9 o'clock in the morning, and then later at noon, it's risen to 65 degrees. So the temperature has swung positive 10 degrees Fahrenheit in the 3 hours from 9 to noon. Then one thing that the intermediate value theorem says is if you pick a temperature between 55 and 65, I picked 60, then at least at some moment, it might be more than one, but at some moment between 9 a.m. and noon, it had to be 60 degrees. The temperature cannot increase from 55 degrees to 65 degrees without taking on every value in between those, in particular without taking on 60. All right, so it's just a little taste of one way to interpret the intermediate value theorem. Okay, let's continue. Last example. Let's use the intermediate value theorem to show that this equation has a solution. I'm going to change color and to emphasize it. We're not trying to find the solution. That's a different question altogether, probably a much harder question, but we've just been asked, show that there is one. Show that there is one. Okay, so how are we going to do that? Well, I'm going to be a little sneaky and pull the left-hand side of this equation down here and give it a function name, f of x. F of x is a polynomial function. It's continuous. It's continuous on the whole real line. In particular, it's continuous on the interval from 1 to 2. It's continuous on all real numbers. That's how I denote all real numbers, is that kind of funny looking R. Polynomial function's continuous on all real numbers, then in particular it's continuous for the numbers between 1 and 2. 1 and 2 I'm not choosing randomly, certainly not picking them randomly, right? But now let's evaluate this function. Help me out with a little bit of arithmetic here. What is f of 1? Plugging in x equals 1, you get 4, take away 6, plus 3 minus 2. So what is that? That's negative 4 plus 3. That looks like negative 1. F of negative 1. Sorry, f of 1 is negative 1. And now let's check out f of 2. Let's check out f of 2. Arithmetic's a little bit harder this time. 2 cubed is 8 times 4 is 32. 2 squared is 4 times 6 is 24. 3 times 2 is 6, and you got to subtract 2. All right, so maybe you should pause the video and do the arithmetic. You can probably do it faster than me. 32 minus 24 is 8, plus 6 is 14. Take away 2, that's 12. Okay, and you're saying, Dr. Evans, why are you calculating these things? We were asked to show that this equation has a solution on the interval from 1 to 2. Well, look what we just did. Let me point out, I'll draw a picture, but negative 1 is a negative number, 12 is a positive number. So if I drew sort of a little pseudo graph of what's going on here with this function, let me mark the numbers 1 and 2 on the number line here. The function value at 1 was negative 1. So the graph was down there. My picture is not going to be to scale, but the point 1 comma negative 1 is on this graph. At 2, it had climbed up to 12. Yeah, the point 2 comma 12 is on the graph. The point negative 1, well, 1 comma negative 1 is on the graph. So I'm going to choose the value of n to be 0. Remember the n in the statement of the theorem? It says if I pick any number between negative 1 and 12, then my function has to take on that value. You can kind of intuitively, a continuous function, no jump discontinuities, no asymptotes, no holes in the graph. How can a continuous function make it from down there at negative 1, 1, all the way up to 212 and not cross that axis? I think my screen has just frozen. I hope this doesn't happen a lot in this class. Oh, there, it kind of popped back. Yeah, good. So I was drawing these curves. Here, let me recreate the drama for you. How can a continuous function make it from down here? Oh, stop doing that. How can a continuous function make it from down there to up here without crossing the axis? It has to cross that axis. All right. So that's why there must be some number, let's call it c, where this f of x is equal to 0. So our equation, in fact, has to have a solution. Okay, thanks for listening.